Okay, so all I did was I actually substituted the values of L equals 1, R equals 6, and C is 1/5, and then I made it so that the coefficient of this term was 1, and so you end up with this differential equation. So, I love checking off things on a to-do list, so I've done it. I found my differential equation, now all I have to do is solve it. How do you solve a second-order differential equation? Well, you do it like you do any differential equation. You've got to first find the natural part, and the natural part's going to have two arbitrary constants. Put a hold on that, then you find the force part, put them together, you've got the solution with those arbitrary constants, and then you just solve for the arbitrary constants using the boundary conditions. That's it in a nutshell. How do you solve the natural part of this? Okay, here's the second-order differential equation. This is what you do. Transform it back using the S operator. So I'll have S squared V plus 6S V plus 5V equals 120. Since we're looking for the natural part of the solution, or sometimes called the homogeneous part, or the transient part, remember there are all those different names for it, that's obtained by setting the forcing function equal to 0. If you do that, then you can divide by V, and then that just drops out. And what you end up with is something that looks very interesting, and it has a name. This is called the characteristic equation of this differential equation. And really, it's very easy to get. It's just, what do you call this? A quadratic equation in S, in the unknown S. The coefficients are the same coefficients as from this is 1, from the differential equation. So really, you could just jump from here to here very quickly. You just take the coefficients of the differential equation, and you set up a quadratic, and then you solve that quadratic equation. So S, the roots, are going to be equal to minus b plus or minus the square root of b squared minus 4ac. So this is all over 2a. So this is minus 3 plus or minus the square root of 36 minus 20 is 16. So that's 8 over 2. Minus 3 plus or minus 4. Did I do that right? Yeah. No, something's wrong. 6 divided by 2 is 3. Because my roots are different. The roots should be minus 1 and minus 5. What did I do wrong? Kyle, where's my mistake?
You don't even have to do, you can just simplify it.
S squared.
S plus 5, S plus 1.
So you just by factoring it? Okay, so I obviously screwed up my quadratic formula. But yeah, we could just factor it. S plus 5 and S plus 1. Yeah, that'll do it. Okay. So there we've got our roots. Thank you. So S, why didn't my quadratic work? I should have gotten the same answer. Okay, I obviously made some mistake. So S is minus 5 or minus 1. So this is kind of the same idea as here, where we're going to have 3 cases. If we have the standard RLC circuit, we calculate alpha and omega, and we determine which case we have for the natural solution based on, whether alpha is bigger than omega or equal to or less than. Here, when you get the roots, the 3 cases are dependent on whether you get distinct roots, which I have here. If you have distinct roots, okay, so let me do here. So if roots are distinct, then we have the overdamped case. And so this is the form of the equation that we'll have. And just to make it a complete presentation here, if the roots are the same, in other words, indistinct, like if somehow, we got, the same root, that's the critically damped case. And then if we have roots that are imaginary, then we've got the underdamped case. Okay, so, and the formulas are the same as here. Overdamped, critically damped, underdamped. So we have the overdamped case, because I look at these roots and I'm like, oh, okay, these are distinct roots, so I've got the overdamped case. So I know that the natural part of my solution is, and I don't have to say X because I know that I'm looking for my voltage. So the voltage, the natural part of the voltage, the solution to this differential equation is A1 E to the S1t, so that's, I'll take minus 1 first, so to the minus t, plus A2 e to the minus 5t. So there I have it. There's the natural part of the solution. It's got two arbitrary constants. Am I going to try to calculate those constants right now? Absolutely not. Don't even be tempted. You've got to get the complete solution first. And so to get the complete solution, I need to get the forced part as well. Okay, so how do I get the forced part of the solution? And I'm going to erase this here. Well, we could do it mathematically, or we could do it the way I did at the very beginning of this problem, which is because it's a constant forcing function, and I go back to this problem, this is a constant source, really, you can do it by inspection. You could just look at the circuit and say, okay, after a long time, the capacitor acts like an open circuit, the inductor acts like a closed circuit, so all of these 4 amps are going in this branch. The voltage then is going to be just the voltage across that resistor, 4 times 6, it's 24. So you could do it by inspection that way, or if you wanted to do it mathematically, which I do because I want to show you how to do it when it's not a constant function. What you do is you go back to the differential equation and you guess a solution. Okay, and the solution that you're going to guess, you want it to look like the forcing function on this side. What does the forcing function on this side look like? It's just a constant. So let's just call it K. I'm going to guess that my solution is a constant. If this were a sinusoidal, I would have guessed like, you know, a general form of the sinusoidal. If this was an exponential function, I would have guessed an exponential function that looked like it but had some constants in it so that it's like the most general form of whatever exponential function that was. So that's the idea. And if you do that, then what you do is you just plug this back into the equation. The first derivative then is 0 of a constant, right? And the second derivative is 0. So you plug that back into the equation. Let's see, so I get 0 plus 6 times 0 plus 5 times k is equal to 120. K is 24. Get the same answer I did by inspection. But I wanted to go through this process because this is the process you'd have to go through if it wasn't constant. But this was constant, so we could do it either way, either by guessing a form of the forced response that matches the forcing function and plugging it in and then just solving for the constants, or in this case, because it is a constant source, we just did it by inspection. So here we've got it. The natural part and the forced part of the solution. Now we put them together and we get the complete solution, right? Which is just the natural plus the forced. And actually, usually F first. And because this eventually is going to drop out, right? So this is equal to 24. Okay, let me put it here. So we're almost done. V of t is equal to 24 plus a a1 e to the minus t plus a2 e to the minus 5t. So we've got our answer. I mean, we pretty much solved for v of t for all t greater than 0. The only issue now is that we don't know what these two constants are. So now is the time. Now is the time to find the arbitrary constants, because I found the natural part, I found the forced part, I've now got the complete part, but it's got those arbitrary constants in it. So now I'm going to solve for those arbitrary constants. So I need some boundary conditions. Usually the boundary conditions are the initial conditions, but not always. Sometimes you might have some information about your circuit, like maybe at t equals 3 seconds, you happen to know what the voltage is. I actually didn't put all of the given information in this problem. So let me go back and point out to you that at t less than 0, this is 0. There is nothing driving this circuit. So if we presume that it's been like that for a long time, then both the initial current here through the inductor is 0, and the initial voltage is 0. So these are the boundary conditions, and in this case they happen to be the initial conditions that I'm going to use to solve for A1 and A2. Okay, I'm going to warn you right now that one of the conditions is very easy to apply, and it's the second one that's going to give you the headache. So just be aware of that. Okay, cut.